welcome to another exciting round of Multiplying Mayhem. I'm your host, Mayhem Matt. Let's get started. Well, today we're going to do something that I never thought I'd get a chance to do. People are always asking me, Matt, when are you going to do an episode on the principles of conservation of mechanical energy to find the final velocity of an object? Well, today, my friends, is that day. And you and I are here at the fabulous New York Hotel Casino in sunny Las Vegas, Nevada. We're here at the Coney Island roller coaster, and here's the question we want to find the answer to. See that big hill behind me? We want to know what the final velocity of the Coney Island Express is at the bottom of that hill. Now, you get into the front of the roller coaster, and you've got your speedometer, and it's working just fine until halfway down the hill. Then, it explodes upon impact. We don't know why. We don't know how. It doesn't matter. But how are we going to find the final velocity now that the speedometer's broke? Well, that, my friend, stay tuned, and we'll find the answer together. I'm Mayhem Matt. See you in a minute. All right, well, we are back from the Coney Island Express from the New York Hotel and Casino. And if memory serves, we were talking about how to find the final velocity of the Coney Island Express. We said that our speedometer melted down or whatever happened halfway down. So now we have to use the principles of conservation of mechanical energy to find the final velocity of the Coney Island Express. So let's just start off with, what does the principles of conservation of mechanical energy really mean? Well, textbook definition just says if the net work being done on an object by non-conservative forces is zero, then the total mechanical energy of the object has been conserved. So what does that really mean? I mean, that's a great definition, but how does that apply to us and the Coney Island Express? Well, I'm going to tell you right now. Now, don't be jealous of my artwork because it is something to behold, I know. So let's just say that this is our Coney Island Express at the top of the hill, right? It's stopped. Well, from here to the bottom of the hill, there's no friction. Right? Because friction is a way to deplete energy, right? Heat. Think about like brakes on your car. When you keep applying them going down the hill, they heat up, right? You lose energy that way. So that's not being done here, okay? This is our halfway point, and we said that this is where our speedometer just went kapooey. We want to find the final speed here at Y. So now that we know what mechanical energy is, let's talk about what makes up mechanical energy. We need to know what mechanical energy is comprised of. So let's say that we've got mechanical energy here, and this is our abbreviation, mechanical energy. I know, pretty high-tech stuff, ME. Well, the first part is potential energy, isn't it? Well, what is potential energy? Well, in the Coney Island Express, think about it. It's when the train comes out of the station, rolls around real smoothly, connects up to that chain, right? And then the chain pulls it up and up and up and up and up and up and up the hill. At the top of the hill, that is the potential energy. That's the most potential energy the train's going to have, right? So let's stop it right there at the top of the hill. What else makes up mechanical energy? Well, that's kinetic energy, isn't it? And that's just energy in motion, right? Once the train goes down the hill, isn't that when we start picking up speed? It most certainly is. So as you can tell now from that conversation we just had, what kind of relationship do these guys have? Yeah, they've got an inverse relationship because as this goes up, the potential energy goes down. As potential energy goes up, the kinetic energy goes down. And keeping in balance for total mechanical energy. I know it doesn't get any more exciting than that. Wow. Well, what's the next thing we probably need to discuss? Formulas. You knew I was going there, right? So let's talk about the formula for potential energy. And that's just going to be simply mass times gravity times height. That's for the potential energy. Kinetic energy is going to be 1/2 times mass times velocity squared, isn't it? Yeah. Now, if you see 1 and 1 here, 1 by the V, 1 by the H, that's called sub 1. You'll hear people say sub 1, sub 2, sub 3. That's what that means. 2 right here, the V being squared, that's called superscript, just so that we know what we're working with now, okay? Well, remember just a minute ago when I said we don't have any friction from the top to the bottom? Well, since that's the case in our particular instance, we can set that equal to itself essentially, right? Just mass times gravity times height plus our kinetic energy, which is 1/2 times mass times velocity squared, right? Just set itself equal. This is the top of the hill. This is the bottom of the hill. Really pretty, relatively simple, isn't it? Well, what are we solving for? Well, we're solving for this V, aren't we? The final velocity, right? Because I've got my subscripts over here, right? H sub 2, V sub 2, right? Right. All right. So looking at the right-hand side, the RHS, Is there anything that we can get rid of that we don't need? Well, you know there is, or I wouldn't be asking, right? Well, what about this height here? Well, we know the final height is going to be 0, right? From the top of the hill to the bottom of the hill, at the bottom it's going to be 0. So we can get rid of that term. So let's move over here to the left-hand side. Is there anything that we can get rid of on the left-hand side? Well, I'm looking at that velocity because what's the final velocity? It's going to be 0, or I'm sorry, our initial velocity is going to be 0, isn't it? Right, it's in the train station. It's not doing anything. It's not moving unless the operators are tweaking with the switch, moving the train a little bit back and forth while people are trying to get in, and then they start tripping all over each other. I don't know that that's going on down there, but don't hold your breath. It might be. Anyway, we can get rid of that term as well. So what does that leave us with? Well, let's clean this up, and let's see what it leaves us with. So we've got mass times gravity times height, and that is going to be equal to what? Our kinetic energy over here, which is going to be 1/2 times mass times velocity squared. All right, well, we're whittling away at this relatively easy, aren't we? Look, we went from this to this in one fell swoop. We're trying to solve for v here, the final velocity. We don't know what it is yet, right? All right, so that being said, we see we want to solve for the v. We want to isolate the v, but we've got a fraction over here. Well, if you know Mayhem Matt sees a fraction, you know what he's going to do. Yep, he's going to get rid of it. How does he get rid of it? Well, the 2's being divided over here. The 1's being divided by the 2. So let's multiply it by the 2, right? And that's going to get rid of the 2's. But you've been hanging out with me long enough. You know where I'm going. If I do it on the right-hand side, I've got to do it on the left-hand side. So now, this is what we have. Well, let's clean this up again so we can see better what we're working with. And that is equal to 2 times mass times gravity times height is equal to mass times velocity squared. Man, we're getting close to isolating that v. Can we get rid of the m's? Yeah, we can. They're being multiplied. Let's divide them. So here we go. Both m's gone. Let's clean this up again. What are we left with? Well, we're left with 2 times gravity times height, and that is going to be equal to velocity squared. I want to solve velocity, though. I don't need velocity squared. I need to know what v is. How do I find out what v is? Yeah, you're right. I can't take the square root of it, so let me do that. But hold on a tick. If I do it over here, you know I got to do it over here. Does that make it worse? No. I'm going to show you why here in just a second. Watch. All right, I'm just going to flip these terms around. I'm going to put the v over here, and I'm going to make that equal to the 2 times the gravity times the height. I'm going to get rid of this radical sign, don't I? There's only room for one radical person on this show, and that's me, not here. So let's get rid of this. How do we do that? Well, what if I just square that up here, right? There's an implied 2 here. If I take the 2 up here, then that gets rid of the radical. Now, I'm just equal to v equals 2 times gravity times height. Can we solve for this? Yeah, we've done this numerous times. We've seen so many algebraic equations. This should be anything. So get out your handy-dandy calculator and take 2 times gravity, which is going to be 9.8, times the height. In our case, that's going to be 400. Take the square of that, and that's going to give you what? Yep, about 89 meters per second, right? 89 meters per second, or what? 198 miles per hour. That should be fast enough for anybody. Well, that's all the time we have for here on Multiplying Mayhem. You've been a wonderful audience. Thank you so much for joining me today, and we'll see you next time here on Multiplying Mayhem.